Math 2415, Calculus 3, Multivariable Calculus, Chapter 10, Vectors in the Geometry of Space, Section 8, Arc Length and Curvature, Video 3, the arc length function. Question, given a parametrized curve, and since we're in 3 dimensions, that means we're going to have x, y, and z component functions, most likely called f of t, g of t, and h of t. But given a parametrized curve, can we define a formula that calculates the arc length as a function of the parameter? In other words, can we derive a function that answers the question, how far has a particle traveled after a certain amount of time? That would be a good piece of information to know. How far have I traveled after 1 second, after 60 seconds, after 1 year, if I know the path that I'm going along? Well, the answer is surprisingly straightforward. The answer naturally lies in the arc length function, but we kind of have to set this up a little bit more carefully. Let's say that we have this space curve, okay, that's defined parametrically. And let's just say that it goes on ad nauseum. But we do have an initial point. So let's say our initial point is at t equals, well, should we make it t equals 0? How about let's be generic and make it t equals a? And then we have our parametrized curve, parameterized by r of t equals f of t as a vector function. First component is f of t, second component is g of t, and third component is h of t. And I guess we can go ahead and parameterize it on some closed interval a to b. So we'll go back and change this to having a terminal point, excuse me, where t is equal to b. And let's say that we want to know how far have we traveled at a certain value of t. So at a given value of t, what is the arc length? Well, let's call the arc length formula s of t, or the arc length function, I should say, because s kind of looks like an arc. Well, if we set up our integral, it's just from a to our stopping point, but we want the stopping point to be some random t value. So we'll put a t up there. Well, this raises a problem because we can't integrate with respect to a variable that's a limit of integration. In other words, if t is the upper limit, we can't write dt or have a t inside of there. So we just need to change the variable. We'll change it to u. Why? Why not? I'm using u because that's the one that's in our current book. So our arc length function is simply, let's integrate from the initial point to some variable t, and then the magnitude of, or the speed of the particle, the magnitude of the derivative, if you will, magnitude of the velocity, if you will. And then we'll just create a function that answers the question, how far have we traveled? So for example, if we go back to the function that we had before, r of t is equal to cosine of t, sine of t, and then t. Let's widen that. But we need a specific interval. So let's say from 0 to 2 pi. And then we want to create our arc length function s of t, defined on t in the interval 0 to 2 pi. Okay, so when you make an arc length function, it's only defined on the interval over which the arc is defined. All right, well, we do pretty much the exact same thing we did before. The only difference is, I'm not sure what just happened there. The only difference is, stop that. I'm trying to change color on something. The only difference is when we set up our arc length integral, t is now going to be the upper limit of that integral, with 0, the beginning of our interval, being the lower limit of the integral. And we're still going to do the magnitude of the derivative, but now we're just going to do it as a function of u. My u's are looking very v-like. I'm trying to make them a little curvier. I guess I could use v. It really doesn't matter as long as I'm consistent with my variable. Well, what we just did earlier isn't going to change. In other words, in the previous video, when we found the derivative of our vector function, it was negative sine of t, cosine of t, 1. And when we found the magnitude of that, it ended up being just the square root of 2, because we end up with the sine squared plus cosine squared plus 1 under the square root. So we're going to integrate the same function. It becomes independent of the the variable that we're integrating with respect to. In other words, there's no u's in here, just the square root of 2 du. But when we integrate that, we get the square root of 2u from 0 to t. And so we end up getting the square root of 2 times t. Therefore, if you want to tell me how far I've traveled along this curve at any moment in time, all I have to do is take that time and multiply by the square root of 2. Now, it's not always that simplistic, but, you know, the first example usually has to be pretty straightforward. Actually, it is that simplistic. If we can find the specific arc length from a specific A to a specific B, it stands to reason we could find a generic arc length from a specific A to a generic B. In other words, from wherever the curve starts, which in this case was 0, to a random stopping point t instead of a specific stopping point like 2 pi. And then you just run the integral out the way you normally would.